Thanks to one of your peers, I realized that I didn't post lesson 10.7. I thought I already had, so sorry about that. If any of you need extended time, that's okay. I really just want to try to get through chapter 10 by the end of next week. So I just have 10.7 and 10.8, some type of review, time to talk to each other, time to ask me questions, and then I'm going to give you an assessment of sorts. I got to come up with that yet. By the end of next week. So 10.7 goes along with 10.3. I'm going to say it's the opposite. It's not the right word, but in 10.3, you learned about some special products and what happened with some patterns. So this is when you are changing something that's in standard form and has a special pattern and you are factoring it or putting it into factored form. So there are a couple patterns to look for, and 10.8 has a lot to do with this as well. And 10.8 is factoring in general, factoring a lot of different things. So while 10.7, the assignment might be kind of easy because you know it fits the patterns, 10.8 is pretty random. So some of it will just be factoring and some of it will be a special pattern that you can factor, and it'll be mixed together. So 10.8 is a little more challenging, and I'll call it fun. So there are some specific patterns that you should notice. So one pattern is called the difference of two squares pattern. I just learned it as difference of squares. So if you notice, when you look at the problem, the directions will just say to factor it, so it's going to be in standard form. And you notice that you only have two terms. Both are perfect squares. Sorry. So two terms. Both are perfect squares. And between those two terms is a subtraction sign. Then you know that you have what's called difference of squares. All right, so problem might start something like this. You see you have two terms. 9x squared is a perfect square. 16 is a perfect square separated by a subtraction sign. Then when you go to factor that, it's just an expression. So when you go to factor that expression, putting it into factored form, you just take the square root of the 9x squared. Okay, so what times itself will give you 9x squared, and it would be 3x. Take the square root of the 16, and you get 4. And then notice in your factored form, you have 3x plus 4 and 3x minus 4. So one will be addition and one will be subtraction. Okay, so really you're just finding the square root of 9x squared equals 3x. The square root of 16 equals 4. Putting them in two sets of parentheses, 1 plus, 1 minus, and then that is your factored version of 9x squared minus 16. I'm going to go all the way down to example 1 just to take a look at what this one would look like then, because it fits that pattern. Perfect square, subtraction sign in the middle. What's the square root of m squared? Just m. What times itself makes m squared? M. What's the square root of 9? 3. You're going to set up two sets of parentheses. The m in the front, the 3 in the back, one with a plus, one with a minus. Boom. Now, you can check your work. It's kind of cool. I told you this goes along with 10.3. So if you were to multiply this back out, okay, use the distributive property twice. M times m. I'll just draw the little, right? M times m, m squared. M times negative 3, negative 3m. 3 times m, positive 3m. 3 times negative 3 is negative 9. Notice these will always be opposites. So when you have those as opposites, they will just disappear. They'll be 0, and that's why you end up with the m squared minus 9. Okay, but anyway, back to the problem. Problem looked like this. This was expanded form. Your answer is factored form. the m plus 3, m minus 3. Okay, I was just explaining how you can check your answer to see if that's right by multiplying it back out. You should get that m squared minus 9 back again. Okay, let's just do one more and stick with that pattern. So you see a perfect square, you see a perfect square, you have a separation of a subtraction sign. You do square root of first term. I don't have to show that work. I'm just telling you that you have to find what times itself makes 49. That's 7. What times itself makes q squared, q. Okay, so you've got a 7q. What's the square root of 81? You can ask yourself that in the head, your head. Square root of 81 is 9. So your factored form, 2 sets of parentheses, the 7q in the front, the 9 in the back, or as your second term, 1 with a plus, 1 with a minus, and that is your factored form. It equals this expanded form, factored form. You factored that expression, okay? This is two things multiplied by each other. The 7q plus 9 is a factor, the 7q minus 9 is a factor. Factored form of 49q squared minus 81. Okay, so that's one pattern that you're going to see or notice. 10.7 is not going to be that difficult because they chunk the assignment and then put all of the same kind of pattern pretty much all together, and so you keep doing them the same way until you get it. The other pattern is called perfect square trinomial pattern. Maybe not as easy to recognize when you can do it and when you can't do it, okay? But you're going to have, notice in this one that you have 3 terms. I'll write it out like I did this one. So things you should notice about the pattern. You have 3 terms. The front term is a perfect square. Back or last term, I guess, front, back, last, third term is perfect square. Those are your biggest indications, because when you look in the middle term, it's kind of weird. But it is going to be 2 times the square root of your first term, I guess, because you see how it just says a. And I'll say square root of third term. That's how you're going to recognize it. Perfect square in front, perfect square in back. If you take the square roots of those two things and multiply it by 2, you get the middle term. Let me look down here. X is a perfect square. X squared is a perfect square. 16 is a perfect square. If you take the square root of x squared, you get x. If you take the square root of 16, you get 4. The 8x is 2 times x times 4. Sorry, my finger got in the way there. Okay. So when you go to factor it, you basically just take the square root of the front term and the square root of the third term, put them inside parentheses, and in this case, because you have an addition between the first 2 terms and between the last 2 terms, you put an addition sign, and it's the square of a binomial, so you're going to put a little 2 outside what you've created here. There's an example right here with a subtraction sign. So let me see if I have, let's go to example. Oh, those both have subtraction signs on them. All right, I'll just explain it with a subtraction sign as well. Okay, so 2 addition signs, you make it addition. This is the exact same pattern, but with subtraction. Remember, if you go back to lesson 3, when there was a subtraction in the front, the back will always be a plus, because a negative times a negative is a positive. Okay, so this back will always be a plus, whether it's subtraction or addition. But when there's subtraction in the front, same exact process. It's just, it's going to be a subtraction in your factored form right there. Okay, so this will be subtraction versus addition. All right, so here's what you're looking at. Here, and this is what you need to notice. Perfect square, perfect square. When you take the square root of x, or x squared, you get x. When you take the square root of 36, you get 6. When you multiply 6 and x times 2, you get, boom, 12. Okay, so when that happens, you can just take the square root of the first term, the square root of the last term, boom, boom. And because there's a subtraction sign in the front, you put a subtraction sign. And the little 2 literally just means the same as what I'm writing right now. Right? And you could write it this way. That's the factored form. Or you can just write it as x minus 6 and then square it times itself. Okay, so let's go look for that in example 2. Turn your page. Let's just change one of them. Let's change this one to plus. Okay, change that to a plus so that you know what I'm talking about when I do this. Here's what you need to notice. Perfect square, perfect square. If I take the square root of x squared, I get x. If I take the square root of 16, I get 4. This middle, if I do 2 times x times 4, okay? So that's what the pattern looks like. That's just what you're checking. Hey, can I use one of my patterns? Oh, it fits that, so yeah. And when you do it, there's 2 plus signs. It's going to be squared. Put a plus sign. Square root of the first term, square root of the last term. Again, if you're all like, whoa, how does that work? You can multiply it out. X times x, x squared. X times 4, 4x. Oh, see, there's the same thing right there. That's why it's double. That's why it's times 2 in the middle. Okay, that is me just checking my answer. Your answer, the factored form, is that. Okay, B, factor it. You've got a subtraction sign, subtraction sign. It's the square root of x squared, x, square root of 4, 2, done. I think I've explained the rest of it a lot, so you can rewind this, go back and look. My husband told me I'm old school because I keep talking about videotaping things and rewinding, but I'm recording and you can go back. Okay, example 3. You might be stumped. Take a look at that. You're like, this does not fit any patterns for 10.7. This is not either of the 2 patterns that Mrs. Stofflet talked about, because a negative 3x squared is not a perfect square. That negative 3 doesn't fit. Negative 27 is certainly not a perfect square. When we get to section 8 and when you do section 7, you need to look to see if you can take out a greatest common factor first. So take out greatest common factor first. All right, you've got 3 terms there. What can you divide them all by? Negative 3x squared, negative 18x, negative 27. What can you divide them all by? So I'm thinking you can divide them all by a negative 3. So here's, it's like the opposite of the distributive property. Okay, you are dividing everything, if you want it to look like this. That's what I'm doing. Divide everything by a negative 3. The negative 3 goes on the outside of the parentheses. So when I divide a negative 3x squared by negative 3, I will just be left with x squared. Negative 18x divided by a negative 3, negative divided by a negative, I'm going to get a positive 6x. Negative 27 divided by negative 3 gives me a positive 9. Now what I have in the parentheses can be factored further. Okay, so I sort of have done a little factoring by taking out the negative 3. Negative 3 was a common factor of these 3 terms. but I'm going to factor this even further. Don't forget about the -3. It still has to stay out there. It doesn't disappear. Okay, so now this is a perfect square. X squared is a perfect square. The 9 is a perfect square. I have 2 plus signs. The 2 plus signs give me a plus in the middle. The square root of x squared, oops, sorry, no, nothing up there. Square root of 9, 3. I meant to put the 2 out here. I'll rewrite that. -3, x plus 3 squared. That is my final answer. It's the factored form of this expanded form, or that expression. I wrote solve the equation. So if I'm solving the equation and it doesn't look like an equation, what do I need to do to it? Solve. So since it's not an equation, I'm going to make it one. Equals y, right? So if I write equals y on the end of it, and I'm trying to find x-intercepts, we're changing that y to 0. If I write the factored form of this instead of the expanded expression I have right now, I'm going to write -3 parentheses x plus 3 squared. What's going to make that equal to 0? -3, multiply it by x plus 3. I'm going to write it twice because that's what it means to square it. That multiplied by this, multiplied by this. What value of x would create an answer of 0? Well, if I'm multiplying 3 numbers together and I'm getting an answer of 0, one of these 3 things has to be 0. These are the same as each other. What x value would turn this into 0? I think a lot of you can just see it. -3 plus 3 would turn that into 0. So x equals a -3 would be your solution if you were asked to solve. Okay, factored form, I factored it. Careful on your direction. So up here, factor. Down here, we're using factoring to solve. This is your solution, x equals -3. All right, example 4. We have a little formula that's not too bad. An object lifted with a rope or wire should not weigh more than the safe working load for the rope or the wire. You've probably done this before, I don't know, but if you put something too heavy, let's say on a piece of string, right? And the piece of string would snap because the object's too heavy. Same for any rope, or if you've done any boating, or if you've seen any of the big river boats that dock down at Riverside, and you've seen how wide, or I guess the circumference of the rope to tie those boats up. It's pretty big because those boats weigh a lot. So the safe working load, they're labeling that with a capital S, in pounds for a natural fiber rope is a function of C, the circumference of the rope in inches. Okay, so C stands for the circumference of rope in inches. So you're talking, I hope you know what circumference is, right? Distance around the outside of a circle, circumference. So if that's like the circumference of the rope. Here's your equation. Safe working load, take the circumference squared and multiply it by 150. So you're setting up a block and tackle to lift 1,350 pounds safe. What size natural fiber rope do you need to have a safe working load? All right, so we have to lift a 1,350 pound safe. So think about what letter that goes in for, and then the question is what size rope? All right, so the weight is the S because that's your safe working load. We don't know their circumference. All right, I'm just going to use the method that I'm teaching in 10.7. I'm going to tell you that if this were on a test and you didn't have to use this particular method, you sure could divide both sides by 150 and then take the square root of both sides to solve for C. But I'm going to use factoring just so you can see how it works out. So I'm going to subtract the 1350 from both sides. Okay, and then try to divide both sides, or divide both terms, sorry, by 150 to see if I can factor out 150. 1350, I'm using a calculator just in case you want to know. And that equals 9. So 150 divided by 150, remember I'm factoring out the 150, it doesn't go away, it's got to stay out in front. But if I divide by 150, I'll be left with c squared. And I just said that if I divided this, I got 9. Okay, so this fits if I have to factor this. This fits one of my patterns. That's a perfect square, that's a perfect square. This is subtraction. I called that difference of squares, leaving the 150 in the front. Difference of squares has two factors that you visually see. I'm not squaring something. And it turns out to be a c plus 3 and a c minus 3. So if I'm solving and I have three terms, or these are not terms anymore, I'm sorry, 3 factors, and when I multiply I get 0, the value of this c, what would make that 0? -3. What makes this 0? What c value would turn this into 0? +3. Only one of these answers makes sense for the circumference of the rope. You're not going to say the circumference of a rope is -3 inches. Okay, so this answer, 3 inches, it should be the circumference or the safe working load for, it's not what I'm trying to say, the size of the natural fiber rope, sorry, 3 inches. Boom, done. All right, there we go. That's 10.7. I'm putting it out there. Bye.